examples of sequences. First example that we're going to talk about is f of n equals to n over 1 plus n. So we have a function. This is definitely a function. This function f of n is defined from n to r. It means that it takes some values from n, 1, 2, 3, 4. If you don't have any restriction on the domain, you always assume that it starts from 1. So let's follow some steps. Step 1. Find some of the terms of this sequence. Find some terms of this sequence. So n is equal to 1. It means that f of 1 is 1 over 1 plus 1 or a half. Next term, so this is your first y value. This is y value. N is equal to 2. You get f of 2, which is 2 divided by 1 plus 2, or 2. This is your second y value. So see, we're just plugging x values, n values, and then we find the y values. N is equal to 3. You get f of 3, which is equal to 3 over 1 plus 3, which is 3 over 4, another y value. Well, you continue this process. This is your step 1. Step 2, graph this. Graph these terms. To understand the general behavior of your sequence. Okay, here you have your n. On the horizontal axis, instead of x, you have n. And on the vertical axis, you have f of n. Well, okay, here you have n equals to 1. Our y value is a half. 1 and a half. This line continues, guys. N goes to infinity. And here you have 1. Okay, our first term, our first y value is a half. When n is equal to 1, we have a half. This is our first dot. Our second dot, 2/3. A little bit further on here. This is your second dot. Not far away. Then we have our third dot. It's very close to this guy. And then our fourth dot, and here we go. Third dot, the fourth dot, and it continues. Step 3. Find the limit of f of x. F of x. So, why we are finding the limit of f of x? When x goes to infinity, n goes to infinity, the behavior of these two functions are the same. At infinity, they have the same behavior. So the limit of f of n while n goes to infinity is the same as the limit of f of x while x goes to infinity, which is the limit of x divided by 1 plus x, while x goes to infinity, which is equal to 1. So when x n goes to infinity, the limit of our sequence is recall that in elementary calculus we learned about the limit. So this is a recall for you. If you have limit of, for example, f of x divided by g of x while x goes to a, and this is equal to 0 over 0, or if you're taking the limit and it is infinity over infinity, then we apply L'Hopital's rule and we say that, hey, this limit is equivalent to the limit of the derivative of f divided by the derivative of g while x goes to a. And if this guy again is 0 over 0 or infinity over infinity, you continue this process by taking the second derivatives. You find the limit of the second derivatives. And again, if this guy is 0 over 0 or infinity over infinity, L'Hopital's rule says continue this process. Continue taking the derivative until one of the numerators or denominators is not 0 or infinity. So take a look at this case. If x goes to infinity, you get infinity over infinity. So L'Hopital's rule says that this is equivalent by taking the limit of the derivative of x, which is 1, divided by the derivative of 1 plus x, which is 1, or equals to 1. Of f of x in Desmos. So here we have our graph. So we are using Desmos to graph x divided by 1 plus x, and see the difference between the graph of your function when it has x, the domain is r minus -1, and the graph of your sequence. So this is the graph of our sequence. This is the graph of f of n equals to n over 1 plus n. And the graph of f of x, which is x over 1 plus x, is graph of a reciprocal function which behaves like this. Well, the graph is continuous, and because of vertical asymptote, it has 2 parts. So the graph of f of x, the graph of f of n. Graph of f of n has gaps in it. You're not allowed to connect these. You must have gaps. Gap, gap. This is discontinuous. This is discrete. This is the topic that we are discussing in discrete math. The graphs of functions that has gap in them. There is no gap. No gap. Just connect all of these dots because x belongs to R. You're allowed to plug in x equals to 1, x equals to 1/2, x equals to square root of 2, you're allowed to fill in the gaps. And note that x can be negative, x can be positive. Here n belongs to n is in n, counting numbers. Counting numbers is not negative. It starts from 1, 2, 3, 4, and so on. Here x is in R minus 1. So there's a difference between the graphs of a sequence and the graph of a function with different domains, but note that at infinity, when x goes to infinity, when n goes to infinity, the n behavior are the same. More examples for you. This was our first